So now we'll move into section 14.4, which discusses the arc length for vector valued functions. So suppose we want to find the length of a curve that's defined by a vector valued function. So we have this lovely space curve, and there's the maple code for it if you want to see it. And we want to find the length of this curve. So if we interpret the curve as a trajectory of a moving object, so say you have a moving object that's flowing around that path, then the length of that curve can be thought of as what feature of the motion. So let's suppose you have an object right here and it goes around through the curve. This is kind of a Pringle shape. Looks like an elliptic paraboloid. That would be the length of the curve would be equal to the distance a point travels on the curve. Or in other words, the distance traveled. All right, now how would we find that distance? So from algebra, we've learned, and I remember learning it this way. I remember learning in algebra that distance equals rate times time. But of course, we learned in calculus, so this is algebra. But in calculus, we learn, not quite. The rate thing is a little weird. So we make it distance equals velocity times time, right? So it implies in algebra that your rate is constant, your velocity and it's only in one dimension. Right? But in calculus, we learn that there's a little bit more going on there. We learn that distance, which is position, is a little bit more complicated than just distance equals rate times time. That only works if you have a constant. But if you don't have a constant, which we don't most of the time, you're going to take your velocity and you're going to integrate it in order to find your position. And that gets you, displacement. And from there we can derive position. So I'm going to put like squiggly equals into there because they're related to this. So if you remember really quickly, if you have displacement, if you say the curve is your velocity function, so if I say that's v of t, then displacement would be the integral of v of t, like that. And then distance is actually the integral of the absolute value. So the first part's the same, but that little low part goes up and they take the absolute value. So it's the absolute value of v of t. And you take the integral of that absolute value. So displacement is the integral of velocity. Distance is the integral of the absolute value of velocity, right? So we should have learned all of that in Calc 1 at some point. So position is related to velocity, related to displacement. So position is related to displacement and distance. There's a little bit more going on there. It's not quite as simple as distance equals rate times time or even distance equals velocity times time, because that assumed that the velocity was constant. But if the velocity is not constant, which it is not here, or I guess it could be, but we generally don't assume it is not constant necessarily. I mean, it could be, but that would be kind of a boring problem. So that velocity right there, if you take the integral of velocity with respect to time, you'll get displacement. And displacement is the area between the velocity curve and the x-axis or the t-axis. Distance is the area between the absolute value velocity curve and the t-axis. But what if we're not moving along a straight line? Oh, and this is all still one dimension. Right? That's what we assumed in Calc 1. So in Calc 1 and Calc 2, we were doing everything still with motion in one dimension. But what if it isn't? Okay, well then your rate would be your speed, which is the absolute value of your velocity vector, which of course is the absolute value of the derivative of your position vector, because the derivative of position is velocity. So that would get you your rate. And then your distance would be the integral, not of absolute value, well, I can do it this way, absolute value of velocity. In other words, it's the integral of the absolute value of the derivative of your position vector with respect to time. Since this is our distance, and we've already established that distance will be the point traveling around this curve, it'd be the length of the curve, then that means that this integral right here, that is the distance, would also be the arc length, which is the formula for arc length right here for a vector valued function. So the formula for arc length for a vector valued function is equal to the integral from a to b of the derivative of position. In other words, it's the distance that a point would travel. All right, so making some connections to Calc 1 and Calc 2 and so on. In Calculus 2, we saw that there are two other forms of the arc length integral. Discuss each form and why it makes sense in the context of the arc length integral we just found above. Okay, so hopefully you saw this in Calc 2. This was one of the forms for arc length. So if we look at form 1, let's define our function. If we say x is equal to t and y is equal to f of t, then together that's a parametric form of f of x, right? Okay, so then when we look at position, r of t would be equal to t f of t. And the derivative, r prime of t, would be equal to, well, the derivative of t is 1. The derivative of f would be f prime of t, whatever the heck that might be. All right, so putting this all together, how does this form our arc length? So if we look at the arc length form that was given to us in Calc 2 right here. So there's the form, and I say that this is equal to L. Then L is equal to the integral from a to b of, actually I'm going to go in reverse here. So it would be the integral of this derivative, absolute value, dt. We already said that up above. I'm going to work from this one right here into that one right there. And that is equal to the integral from a to b of, okay, so according to well, calculus, the absolute value is the magnitude of the vector. So it'd be the square root of, now my derivative is right here. So it'll be 1 squared plus f prime of t squared dt, which is the same form as in Calc 2 above, right? So this is from Calc 2, and we just proved that the yellow one up above, this one that we started with, which is right here, is the same form. So there's the yellow one, and that's the same as the Calc 2 one. So it works if you use parametric form. So if you change your position vector into a parametric form equation, and then you have it. All right, now what about the other form that we learned, which is that if you define your curve parametrically in x of t and y of t, from t equals a to t equals b, we learned that arc length is also this. So that's another Calc 2 form that hopefully you saw somewhere in Calc 2. Okay, so if we think about the square root of x prime squared plus y prime squared, if we notice that r of t is equal to, would be equal to x of t comma y of t, then the derivative would be equal to x prime of t, y prime of t. So therefore, the magnitude of r prime would be equal to x prime of t squared plus y prime of t squared. So then if I look at the form up above in yellow, L is equal to a to b absolute or magnitude of r prime of t dt. That would be equal to the integral from a to b, the square root of x prime of t squared plus y prime of t squared dt, which is the same form as Calc 2. So it all works. So both the Calc 2 formulas that we learned are actually going to work for us in Calc 3. And as a matter of fact, this is another way to view that form up above. Also note that if there were 3 dimensions, so this is 2D, if it was 3D, your arc length would be equal to, from A to B, the square root of x prime of t squared plus y prime of t squared plus z prime of t squared dt. dt. So they're one and the same. Right? They're ways of writing out the formula at the top of the page.